Okay. Okay. Well, we've got quite a crowd up here for this one. The topic of our next talk is taken out of context: language theoretic security and potential applications for ICS. We have three speakers in this. Our first is Darren Highfill. He is the founder and managing partner of Utilisec. Darren's been very active in this field for over 20 years. A lot of you have probably run into him. He has a long history building and leading and facilitating industry efforts such as ASAP SG, the Smart Grid Security Working Group, and a variety of other things. Probably just about any of the electric areas and smart grid areas you've seen Darren. Our next speaker is Meredith Patterson. She is a software engineer at Nuance Communications. She developed the first language theoretic defense against SQL injection in 2005 as a PhD student at the University of Iowa, and has continued expanding that technique ever since. She lives in Brussels, Belgium, so thank you for the long trip. I appreciate that. And here we go. And Sergey Bratus, the third speaker, is a research assistant professor at Dartmouth College, and he coined the term weird machines, which you'll hear about in this presentation. So please welcome our three speakers.
All right, thank you, Dale. So if any of you have been to previous S4s, you've heard me talk about some of the more head-scratching, applying some academic theory concepts to real world scenarios. Talked about using use cases, using finite state machine analysis. All of that really kind of led me into this area, looking at language theoretic security. And this is really, I think, the first time that we're starting to look at applying these principles to the SCADA sector. And so I think there's a lot of potential here. I've got need to do a little bit of, ironically enough, context setting here, so that you know where a lot of this is coming from. We're going to start out talking about the problem of how do you know when you receive input? How do you know that that input is safe to deal with? So far, the vast majority of ways that we deal with this is we go through a trial and error approach. Basically apply Darwin's theory. Don't open the package that looked like the one that the last guy opened. He blew up. So you develop this list of rules of don't do X, kind of a blacklist sort of thing. The other way that we primarily trust a package is we decide, we're going to trust the source. This one actually showed up, was delivered by UPS, looks like it came from my grandmother, it's somewhere around the time of my birthday. Alrighty, I'll roll the dice and open this one. We have started exploring some whitelist kind of approaches in certain areas, but I don't think we've taken that far enough. We're not at a point where we can arbitrarily say, given specific input, we can really figure out, what's behind it. Some of this, covering into some of the deeper foundational concepts here, this is really grounded on the halting problem that Alan Turing did so much relevant and foundational research on. Basically, if your boss hands you a stack of source code and says, "How long is this going to take to run?" Can you answer that? Can you answer that question? For really short, really simple snippets of code, you can come up with some kind of reasonable estimate. For much beyond that at all, things get out of hand extremely quickly. And actually to the point where you may not know if it's going to ever quit running. And actually one of the core foundational challenges of modern computing, Alan Turing proved that you can't develop a universal algorithm to determine if a program will quit executing or not. because you can actually turn that, if there was such an algorithm, you could turn that algorithm on its head and prove the algorithm wrong. So one of the other concepts that we'll touch on here is the difference between parsing and processing. And this is one that I think we're particularly bad about in this industry. We tend to mash parsing and processing together. So if somebody hands you some input, how do you determine, can you determine if that input is valid? Well, if you know beforehand that the input is going to be 64 bits long and it's going to be all alphanumeric characters, you actually stand a pretty reasonable chance of being able to, to look at that input and say, yes, this input is actually valid. So you can hold it up to something to determine if it matches or not. If you've got several choices, maybe there's different types of input, and those different types of input can take different patterns. Things start to become a little bit more complex. You got to start to introduce a little bit more logic to it. If your input if determining whether that input is valid depends on processing part of that input. In other words, a length field. You have to, I'm going to give you a packet that in that packet, it's going to tell you how long the rest of that packet is. Now you've got some real challenges on your hands. Bottom line is, it boils down to, do you have to execute any kind of if logic in the process of determining if it's a valid packet or not? So one of the things that my co-presenters here will talk about here in a little bit is some of the research around doing that separation of parsing from processing. It turns out it's achievable, although can be kind of tough in certain circumstances. Can but the bottom line is where if somebody hands you sufficiently complex input, you don't know whether that's actually just data or whether there's an executable hidden in that. We're also going to talk about something, one of the horrid ways that we implement this mashed together parser and processor. We do shotgun parsing. Basically that means that, all right, we've got this blacklist of don't do X, don't do Y, don't do 23. And you accumulate that, and because most of our implementations are built by SCADA engineers, not necessarily software engineers, and definitely not software security engineers, they add that bit of checking or that bit of functionality to wherever in the code it actually makes sense to them. They lump it in with that's where in the code I'm dealing with that aspect of the input. So you wind up with this shotgun pattern of input checking all over the code base. Now, sure, if you have a dense enough pattern, you do enough of that checking, sure, you wind up eventually getting pretty good coverage, but the attacker only has to find that one spot in the pattern that hasn't been covered. You're not systematically covering the whole thing.
Also an anti-pattern just from the engineering point of view. This is also an anti-pattern just from the engineering perspective, because as all of this data...
yeah, hang on.
Is it still not working?
It should be on.
All right. Okay. Now it's working. I was just saying. As an engineering problem, this is also a pretty serious anti-pattern, because your code just keeps getting longer and longer and longer and harder and harder and harder to maintain, because nobody can keep all of that state in their head of like what's everything we're checking for.
Right. So it's been interesting to see fuzz testing start to become more and more popular here, because this is really one of the more interesting techniques for essentially automating finding those white spaces between the coverage dots. A lot of this work also stems from foundational concepts around language formalism, specifically work done by Noam Chomsky, defining containment hierarchy for languages. This one's been, I'll confess, really, really challenging for me to wrap my head around. And I'm probably going to get some examples wrong here, I'm sure my co-presenters will lob rotten vegetables at me when I do, but you know, regular languages are the most strict. They're the most basic. They're the most straightforward. If you think about a finite state machine, a very simple finite state machine, that would be a regular language. Context-free is still pretty straightforward, pretty basic, but you can encounter recursion. So you may or may not know, you may have to keep unpacking things, and you may or may not know where the bottom is. Context sensitive is really interesting. It's where you actually start adding in references, like cross-references. So you may not be able to interpret one phrase of the language without going and interpreting another portion. You've got pointers pointing here, there, and everywhere. And recursively enumerable languages, that's closer to spoken language, where you actually have to have a deep understanding of grammar, of semantics, of context in order to understand what's being said. So a lot of this really depends on having how much context is wrapped up in the language, in the package that you're talking about. So I'm going to steal a little bit of Sergey's thunder here and talk about his concept of weird machines. This is, if you haven't, I'm going to point you to the langsec.org. Langsec.org has some fantastic research material, and one of the core concept papers explains this exceptionally well, exceptionally clearly. If you think about return-oriented programming, this is where we're not injecting new code into the space. We're actually taking the existing code and we're rearranging how the order of execution and coming up with new functionality by rearranging the code that's already there. This is distinct from actually just wiping out what's on the device or what's in memory and providing new code. This is basically saying, I'm going to take the tool that you developed and I'm going to turn it on its head and use it for something completely different. So the interesting thing is that this has also been an opportunity for security research and academia to come a little bit closer together. You started running into scenarios where academia was dismissing some papers because, oh, that's just another exploit paper. This is an interesting angle because now the security researcher can say, I'm going to form a hypothesis that there's actually a hidden machine in this bit of code, and then go forward with a formal proof of the exploit being that is proof that hidden functionality is resident in that code. So with that, I'm going to turn it over to Sergey.
Thank you. I should probably get the clicker.
Oh.
So think of a parser, right? A parser is something that eats characters and then somehow on the other end constructs whatever data structure your subsequent code is going to work with. And the problem with this scheme, the problem with the parsers getting exploited all the time, even before it gets to any sort of a deeper logic in the processing, is that parsers are kind of bad at keeping state of what they do. Parsers tend to be where all those buffer overflows actually happen. And here's why this is. A parser is actually a machine driven by the input as if the input were the program. You consume a character if you're a parser, you transition state. You consume another, you transition state again. What if there is some kind of state that you have not actually provided for in your logic in the code, in the parser? Well, you're exploited. And how easy is it to parse an integer? Right? An integer, you just basically consume the numbers, hopefully they're all digits, then you've got yourself an integer. Not true. Apache found that the hard way in 2002 that consuming an integer in the so-called chunked encoding was not so easy. And in fact, this is where they had an integer overflow and they were exploited all over the web. 10 years passed. It's 2013. Nginx, the other engine, finds the same kind of an issue. They cannot parse an integer that is limited by whatever the limitation for the chunked encoding is. And they get exploited exactly the same bug. It took 10 years to notice, even though people have been looking because both are high-value targets. So the first rule about building a parser is that you have to start building it very small with the most elementary parts of your protocol, with the most elementary elements of your protocol, be it integers, be it single bits. Then, your protocol is actually a bunch of things packaged together. So in your parser, you have to take the small parsers for the elements, the simple ones, and then combine them to get a parser for a more complex thing. So you build it up for a complex package, for a complex message, such as a DNP3 message, all the way up, testing every element, every composed element. In the programming languages community, in the parsing community, the parser combinator style is what this is called. And this is just about the only way to be sure that as you are consuming those characters, you are keeping track of your state. You are keeping track in exactly what element of the packet you are. Okay. So you'd ask, but wouldn't that make a parser too slow? And there is this myth, there is this perception that in order to be fast, a parser just has to be this highly optimized and completely unreadable blob of C code. And this is just not true. The problem with the parser that is not constructed from the smaller parsers, building up to a big message that you can still read when you look at the parser code. The problem with those parsers is you don't know where they spend their time. You can't actually profile them properly. So as Apache and Nginx are both exploited quite a number of times, AT exploits for Apache in just 2013 found the hard way. You spend a lot more time dealing with input that you should have discarded already, burning those cycles unnecessarily. So an HTTP parser proxy, Mongrel, which was built using the state machine system Regal, was actually put in front of the Apache parser as a performance improvement, because it would get to the bottom of a faulty request and drop it, whereas Apache would still continue running it through its bowels. Same story with Nginx. With Nginx, they are using the state machine, but the state machine glums all the states together, whether you're reading HTTP headers, whether you're reading a length, whether you're reading a number. You just can't tell, looking at that code, which place of the code you're in. The parser that is maintainable, that is secure, that doesn't let code propagate through its guts with predictable results, which is ponage, that parser should read like the spec of the language. You should take the parser code and be able to say, this is the spec. I understand what the valid inputs are from this code. And such a parser exists. It's called Hammer. It's a parser construction kit. And Meredith will present it.
Sergey makes everything sound so easy. Now we're going to get into the guts of how this actually works out in practice. All right. So DNP3. We all know DNP3, right? I know DNP3 as of a couple of weeks ago, so if I say anything wrong, please forgive me. But okay, so 3 layers in DNP3. You've got the link layer, you've got the transport layer, and you've got the application layer. DNP3 is also a hotbed of context sensitivity, which we will get into momentarily, but in the link layer, things are actually not so bad to start with. So what we've got here is pseudocode that is really only pseudocode because I left out the type signatures. These are the exact function calls that you would use to define primitive parsers that build up into into a parser for the DNP3 link layer header and then DNP link layer frames. So we start with this with the 2 bytes of sync, which is followed by an integer somewhere between 5 and 255 inclusive. So what does this mean? Okay, well, this hint range combinator says, all right, parse an unsigned integer, an 8-bit unsigned integer, then confirm that that the value of that integer is somewhere between 5 and 255. If it's anything else, throw it out. So if this parser were to see a DNP3 link layer header that claimed that it had a length of 4, it would drop it on the floor. So then you've got the control octet, which I've actually oversimplified. So one of the things that Hammer does that actually no other parser generator library out there does is Hammer is designed to operate on binary formats. It will operate on single bit flags, groups of bits, etc. And if you can find me afterwards, I will happily show you how I broke this out into something that won't fit on one slide. But you can actually see how all the single bit flags for things like the control octet get parsed. So for the destination, that can be any valid 16 bits. Source address again is going to be delimited by value. The CRC again is the value of that will just be some 16-bit int. And then we put it all together in the then we put all the structure together in the rule for the header. So you see that there's a sequence that ignores the start. What do we mean by that? Well, we're not actually going to use those two sync bytes for anything when we process this packet. So the ignore combinator says, yeah, you don't have to actually bother putting that in the output abstract syntax tree. Just make sure that it's actually there to start with. So then that must be followed by the length, which must be followed by the control octet, et cetera, et cetera, et cetera. The null at the end of that is because that's how var arg lists work in C. Sorry about that. But then what is this validate CRC thing at the end here? Okay, well that's a function that you would have to define. So we've got this h-adder-bool combinator, which basically lets you define binary validation functions that operate on the abstract syntax tree of everything that's been parsed so far. So that validate CRC reference is to a function that examines the sync, the length, the control octet, et cetera, and makes sure that that CRC value is actually correct. And if it's not, again, it'll drop that packet on the floor. And I skipped ahead too far. So then the last rule that we've got on this slide is another validated sequence where you've got the header followed by a transport frame, if there is one. There might not be. Followed by end of input. Yes, you can actually specify, there may not be any extra things beyond this. This has actually proven useful in other bugs. The 2006 Bleckenbacher RSA forgery being a prime example. It was possible to forge RSA signatures by just adding extra junk on the end. Yeah, kind of scary. All right, so you'll notice that we haven't actually defined transport frame on this slide. That's because, well, that would deal with the transport layer parser. So we've pretty much gone through everything that was on this slide. So it's also possible to attach what we call semantic actions to parsers. Once you have successfully recognized that yes, a packet is valid in the language that we're dealing with, then it comes the point where you want to structure it into whatever structure you're using in your actual code. And this keeps us from landing in the situation where where we're trying to process data that we don't actually know whether it's really safe or not. Yeah, I was going to say you should take the well-governed feature edition part.
So what's the anatomy of a bug? You've got some code that makes assumptions about what it gets. Those assumptions are supposed to be checked by your combinations of checks, but in fact they are not, or one of them isn't. And this is how you get the buffer overflow, this is how you get integer overflows, this is how you get all the standard little elements out of which you build up your exploitation, your little cogs of the weird machine. Now, suppose that you have a proper parser that validates every expectation that your processing code, which is much richer code, which is where the attacker wants to be, does. And then you want to add a feature. This happens in industry all the time, right? We have seen examples of this in the telecom industry when they actually generate the parser from the spec of the language, something like ASN1, but then something needs to go in. Where do you add that code? Without a model of exactly where your recognition code is, the code that checks all the expectations, you might do what leads to a standard, the most standard of all exploitation variants. You start allocating and copying memory before you've checked all of your syntax. And of course, this is what the attacker is going to hijack in the first place. This is the story of a whole bunch of exploits, pre-auth SSH exploits have gone this route. ICMP version 6 fragmentation exploit has gone this route. Without knowing a clear boundary between your recognition and your processing, you cannot do well-governed feature addition. You have to know what is syntax, what is semantics. The hammer kit pretty much forces you into distinguishing between the two. Because remember, you're writing your parser as a specification for the language. So you have a natural place where you introduce and recognize a feature. But think of it this way. Whatever party you're letting feed you input, that party is causing computation on your system. The more powerful that computation, the more dangerous this computation is, say memory allocation and memory copying, the more likely that they will induce a computation that you're not expecting. So computational power is privilege. Give it sparingly. Premature memory allocation, premature processing is a sin. You are basically exposing that computational power to the attacker and giving it to the attacker. And they are taking it with their exploits.
Okay, so let's look at a concrete example of how this shakes out in practice. So you'll actually see what this bug does when you see Adam and Chris's talk later. So we're not going to give away the entire ballgame here. But all right, so we've got a link layer frame, which has the obligatory prefix, claims that the length is 6. Okay, that implies a 1 byte payload. We've got a control octet, we've got a source, we've got a destination, we've got a CRC, all well and good. Then we get into the transport frame. Okay, we've got the transport control octet. But here's the thing. A transport frame has to have at least one valid APDU in it. If it doesn't, that's an invalid transport frame. This ends up resulting in an unhandled exception, and Adam and Chris were able to do terrible things with this. And we see this over and over and over again in other protocols. You know, as Sergey mentioned, you know, bind, OpenSSH, ICMP. And most of these problems actually end up being caused by non-locality between the length of a field and where that field is actually specified. So I spent a couple of days, well, a weekend basically, not too long ago, implementing a grammar for DNP3. And I have to hand it to you guys. This actually pushed the envelope on the API for Hammer. Like, we actually had to add stuff to the API to be able to handle all of the non-locality for DNP3. So good job, guys. That was that was pretty fantastic. The scary thing is the non-locality in DNP3 actually crosses layer boundaries. Like in octet strings, for instance, when you need to when you need to recognize an octet string, how do you know how long it is? It's specified by the object variation value. Ouch! That means that your parser, 2 layers down from where you started parsing the packet, has to be able to refer back up to its ancestor just to know how many bytes it's supposed to parse. This puts us way, way, way out into heavily context-sensitive territory. There's a paper from Microsoft from a couple of years ago that that talks about the categories that most network protocols fall into. Mildly context-sensitive is the category of grammars where you have adjacent length and value. Like, you know, well, you see that a little bit in DNP3, but mostly not. And really what I realized, like, by the time I'd gotten about 3/4 of the way through, like, implementing all of these objects is, holy crap, we're dispatching on the group and the variation. It's the interpreter pattern. Like, you know, if you know your gang of 4, this is, you've basically got a 2-byte instruction set that you're telling your protocol, okay, follow these instructions that aren't going to necessarily be anything even remotely like any other instruction. You know that. Yeah, it's a lot.
Sufficiently complex input is indistinguishable from bytecode.
Yes, it really is. I mean, it really is. I mean, because you've got bytecode right there in your protocol. You put it there.
Apologize for the juggling here. I've got a podium mic, so I'll let Sergey and Meredith hang on to the mic when we get to some questions here. So how do we actually make use of this? You know, we've talked a little bit about just how complex and context sensitive DNP3 can be. I guess what I would ask you to take away from this is that there are means of addressing that. There are means of dealing with that. There are means of mitigating that. But it takes some very specific discipline, very specific approach, very methodical approach. This is not something that I would ask a SCADA engineer or a SCADA product engineer to go necessarily do themselves or reinvent or whatever. I mean, the idea here is that we want to come up with a library that could be reused by any product engineer, or maybe, who knows, maybe it becomes a bump in the wire that sits in front of a product, kind of like what was done with Apache. The interesting thing to me being that the performance aspects, we oftentimes have SCADA engineers come back to us and say, sorry, security sounds great and all, but I can't afford the speed penalty that it's going to invoke on my system. I'm already strapped to the limits. Well, what if you could reply to them that, well, we're actually going to make you faster by putting security in place?
Although one thing I will point out is that the algorithms for parsing the more complex classes of languages, like the extremely context-sensitive ones, those are going to be slower. Sorry, there's really not much choice. So if you want fast, simplify your language.
So with that, I do want to thank Adam and Chris very much for working with us as we developed this presentation. It was a lot of fun. Very much appreciate them allowing us to give a little sneak preview of their presentation tomorrow. Looking forward to that one. With that, I guess we'll take some questions.
Okay, so let's open it up for questions. Do the first one here.
Adam Crane, Automatic. This question is probably more for Meredith, but with Hammer, there's a lot of talk about memory allocation and creating AppSec syntax trees before you process. Are there any options for doing things with static only memory allocation for embedded systems?
Okay, I didn't quite understand the second half of your question, but let me talk a little bit about about how Hammer does memory allocation. So right now we've got an arena allocator that it basically just carves off a chunk of memory for every new parse. If it needs more memory, it will go and grab it. But allocation within the context of the parse is done off of that chunk of memory.
Okay, so you can do like a memory pool
Right.
type approach.
Yeah,
okay,
exactly.
Very good.
We're actually thinking about embedded is part of the roadmap. We've been working some with Ben Kurtz up in Washington, who does just a ton of embedded stuff, and we've been. The guy that implemented several of our parsing backends actually just recently added a slab allocator, specifically for the purpose of working with embedded.
Perfect. If you have pluggable allocators, I think that would be the biggest thing you'd need for
It's designed to be-
adoption in this space.
It's totally designed to be pluggable. You want to talk to that guy in the hat over there if you want to write a new allocator. But yeah, he designed that part.
Okay, over in the corner.
Is it on? Hi, Anthony Eschpeter with Subnet Solutions again. I've had the unfortunate opportunity of having to write 2 production quality DMP drivers in my time. When I looked at it against the work I've done against the code you had for Hammer, it ultimately looks still like it's to the developer to understand the protocol, the nuances of the protocol, and call the right APIs again to make it work. And I'm wondering if I'm missing something. Is there a higher level concept or construct here that fundamentally reduces the chance of errors that you're working with, or is it a convenient API set?
Well, more of column A, but also a little of column B. So the problem with hand rolling your parser, rather than generating a parser from a grammar specification, is that you can never be sure that you've covered all possible circumstances. Parser generator algorithms are designed so that what you get, after you've fed it a BNF, is a parser that will unambiguously either accept valid inputs in the language or reject invalid ones. So it's totality is what we're going for with Hammer.
So then are you using like eBNF syntaxes or something to describe the protocols and auto-generating the Hammer code, or is it the programmer calling the APIs that is in effect defining that semantics for the protocol?
Right now, the latter, just because we haven't sat down and implemented RFC 5234 yet. That's the ABNF specification that is self-defining. The C syntax is not pretty. I will absolutely agree with that. I mean, we've just finished writing bindings for a whole bunch of other different languages. The Ruby is especially pretty. I'm really happy with Ruby. But yeah, the C is kind of fugly, and I will be very happy when we get to a point where you can just feed an ABNF specification to a tool, and it'll just generate the code for you.
Okay.
But let me add something. Let's think back to the example of a link layer frame, but no APDU. If you write your parser for that, the way we had it on the slide, when you basically specify that these are the elements that follow each other, and then you have one or more of the APDU. This is where you will check it. Or when you construct your parser as, well, a grammar, or if you will, a regular expression at a particular level, because that's what the grammar production would look like, you would not miss that check like the authors of the vulnerable parser did. And you're going to see that on every level of your protocol, on every aggregation level of your protocol. So you are reducing your probability of error just by following that discipline. The checks happen at the right places, not later when it's too late, or not missing because by the time you were writing this function, you forgot what the previous function gave you. You're basically sticking to the specification of the language with its context sensitivity. That's how this method is different from writing your parsers that look nice. Again, if you look at our talk about shotgun parsers, say at Brookon, there is a video at langsec.org. We go through a couple of those really nice parsers. Say the one for the OpenSSH that gave the pre-auth that Goebbels exploited. Very nice parser. Forgot one little thing. Done. Same thing happened with a whole bunch of others. So it's a discipline of where and how, at what point you check your per spec context dependencies.
Okay, and maybe I'd appreciate to maybe talk offline a little bit about it. I mean, your use of the word discipline to me still translate ultimately to programmer be careful.
No.
And I'd love to talk after about how, and maybe it does and I don't see it, how it actually it takes it up a level from that.
What it comes down to is what you're advising the programmer to be careful about. If you're advising the programmer to write a lot of checks, then you're advising the programmer to be careful about stuff that he has to imagine. If you're advising the programmer to be careful that they have implemented every rule that is already defined in this spec, then at least you're giving the programmer something, a positive checklist to go from, rather than, try to imagine everything that isn't an elephant.
Be careful about grammar. Whitelist. Don't try to imagine everything to blacklist.
Yeah.
Coming right back to Darren's original start.
I mean, this all got its start, as Dale said in the beginning, with an approach to defeating SQL injection that basically boils down to context-free whitelisting. And a couple of years later, Bart Purnell came to me and said, "Can we do the same thing for this context-sensitive thing?" And sketches out the Bleckenbacher attack on the back of an envelope, and I'm like, "Oh yeah, actually we can do that." And it's all just kind of blown up from there. This is all whitelisting. It's just not whitelisting in the sense of in the sense of we only recognize these specific concrete attacks. This gives us the ability to be a little more. It gives us more power to express variation in what we're willing to accept.
And also telling a programmer to be more careful about all the bad things to check for, that's really just blaming the victim. That's just about the best way to shift the blame that I've ever heard of, really. Because you can't. Shotgun patterns do not work. Attacker has to win just once.
Okay. Any other questions? So we have one more here.
In your examples, then it doesn't. It wasn't clear to me how your parser trees maintain state. So that would work for one message, but especially in SCADA protocols, then things are often defined multiple messages. So recursing out of the SCADA specific stuff. For example, in the TCP session, we have like the window size amplification header. So if we want to know how big the buffer is, we have to see that on this on an optional header on the send packet. And so in that case, we're building another state machine on top of that that has to do inter-packet state DNP reassembly.
Yes, we are.
So how do you actually handle that and handle lifespans of buffers and stuff like that, so you don't see a fragment start and then never get freed, et cetera, et cetera?
So this is a fantastic question, and unfortunately, it is actually out of scope for this particular library. I'm tempted to say come back when we're done with iterates, because I mean, really, what we've been doing is just kind of cannibalizing all of the good, all of the great stuff that people have been implementing in Haskell. But to answer your question more concretely, we are not trying to address the problem of state across multiple packets yet. Let's get that problem solved first, and we can build up to the next one from there. But yes, I mean that's absolutely a critical question.
Also, if I might add, building a state machine, when what you get out of the recognizer is a clean state, is easier to design, is easier to do. The problem with state machines that sit behind a buggy parser is that you never know at which point it will be entered and how.
Okay, well, thank you very much. Oh, no, we'll break for questions. You want, okay, one more. We have 3 people who travel far. We'll got to give them another question.
Fabian Koch from ABB. Just to have that on camera, could you talk a bit about like licensing of the Hammer framework? And I don't want to use the word roadmap, but some like, what's your plan?
Okay. Well, so Hammer is currently GPL v2. That might change, but the standard library that we are working on for Hammer, which is called Tongs, is going to be BSD. So, come on, I got to make a living somehow, dude.
Okay, well, thank